Hello everyone, I am Subhas Santanam, CSE23444. Today I will be presenting my case study on how vehicle growth and air quality are connected and how they might also impact public health and population density. This topic is not a common or trivial one because it goes beyond just saying pollution is bad. I have tried to explore how different real world factors like vehicle registrations, air quality, disease outbreaks, and population trends are all interlinked. These kinds of connections are usually not obvious, and that's why I chose to study them deeply. To understand this problem from multiple angles, I have used four credible datasets, namely Vaughan, AQI, IDSP, and population projection. All of these datasets are well integrated. They have a common link through state and date or month or year. So, I was able to compare and correlate them across time and geography to uncover deeper trends. I have also cleaned and transformed these datasets for better understanding and consistency. To prepare the data, I cleaned and standardized all four datasets by dropping irrelevant columns and removing missing values. Now, let's take a look at the first question. Are more vehicles on the road actually leading to worse air quality over the years? To explore this, I used three visualizations that compare the total number of vehicles broken down by fuel type with the average AQI across years. In the first chart, total vehicles versus average AQI, we see that from 2022 to 2024, the number of vehicles steadily increased, reaching its peak in 2024. But surprisingly, the air quality didn't worsen with this growth. In fact, AQI dropped to its lowest point in 2024, exactly when the vehicle count was highest. Then, in 2025, the total number of vehicles suddenly dropped, yet AQI actually increased again. This tells us that air quality is not directly or immediately impacted by how many vehicles are on the road. Other factors seem to play a role. To dig deeper, I looked at the percentage change year over year. Vehicle growth decreased consistently and quite sharply in 2025, but AQI only changed slightly and didn't follow the same pattern. This suggests that even when fewer vehicles are added to the road, AQI doesn't automatically improve. In the third chart, the stacked petrol and diesel vehicle plot, both types of vehicles increased from 2022 to 2024 and still AQI stayed mostly stable. But in 2025, when both petrol and diesel vehicle numbers dropped, AQI unexpectedly went up again. So, the takeaway is vehicle numbers alone don't explain air quality trends. Things like fuel type, emission regulation, industrial pollution, and even seasonal effects could be impacting AQI. I used line plots because they are best for showing trends over time, like how vehicles and AQI change each year. I avoided pie charts, histograms, and box plots because they don't show time based patterns clearly. A stacked bar chart helped compare petrol and diesel vehicles in one view with AQI. Now, let's move to the second question. When air quality gets really bad, do more people fall sick with breathing problems? To explore this, I compared monthly air quality data with illness cases related to respiratory issues from the IDSP dataset. In the first chart, AQI versus illness cases, we see both lines fluctuate significantly across the months. But what's interesting is that the peaks don't always align. For example, AQI reaches a low around July to August, while illness cases are actually highest during those exact months. This hinted that the impact of poor air quality might not be immediate. To investigate this further, I introduced a 1 month lag, assuming it might take time for pollution exposure to translate into noticeable health effects. And in the second chart, lagged AQI versus illness cases, we start to see a stronger pattern. When AQI is high in 1 month, illness cases tend to rise in the following month. This is particularly clear in the months of February, July, and December, where the patterns align better after shifting AQI forward. Then I used normalized group bar charts to directly compare AQI and illness cases side by side. With the lagged version, the values are more closely aligned, again supporting the idea that the health impact of bad air quality may show up with a delay. Finally, I broke down illness cases by the most frequent pollutants, and the results are striking. PM10 and PM2.5 alone account for a massive share of total illness cases. These are the most harmful fine particles there, and they are known to deeply affect our lungs. So, overall, this analysis shows that poor air quality does contribute to more respiratory illnesses, but not always immediately. The effect is lagged, and specific pollutants like PM10 and PM2.5 are the main culprits. I use dual axis and group bar plots because they allow me to compare two different variables on the same chart, showing both trends and relationship clearly. I avoided pie, hist, and box plots since they are not ideal for continuous or group time series data like this. Now let's move to the third question. Do places with very crowded population start to face more serious air pollution? To explore this, I used state-wise data on population, AQI, and vehicle registration. In the first chart, total population versus average AQI, I found that as population increases, AQI generally worsens, especially in mid to high population ranges. However, some densely populated states had surprisingly lower AQI, suggesting that strong policies, cleaner fuels, or better emission controls may help maintain air quality despite crowding. Next, I plotted AQI versus vehicles per thousand people grouped by population bins. Here, the correlation was stronger. Mid to high population groups with more vehicles per capita had worse AQI. Yet again, a few very high prop states managed moderate AQI despite high vehicle density, pointing to the role of infrastructure and green policies. I then used a box plot to show AQI across population bins. The mid-high pop group had the highest median AQI and widespread IQR, indicating unstable and poor air quality, likely due to traffic and industrial activity. In contrast, the very high pop group had a lower median AQI and smaller spread, reinforcing that population alone doesn't determine pollution levels. Crowded areas often face worse pollution, but it's not guaranteed. Vehicle density is a major factor, and regions with strong infrastructure and regulation can maintain better air quality even with high populations. I use scatter plots, group plots, and box plots to highlight relationships and variability. I avoided pi and line chart as they don't show correlation or distribution well in this context. Now let's move to the fourth question. Does air pollution get worse when more new vehicles are registered? In the first question, we looked at trends across years. But here, we focus on month-wise data, examining which months see higher vehicle registrations and exploring possible reasons such as festival or season factors. To explore this, I used line charts over time comparing monthly vehicle registrations and AQI. The first chart, AQI versus vehicle registrations, I saw that AQI often rises when registrations go up. However, the match wasn't always immediate. So I created a second chart, lagged AQI versus vehicle registrations, shifting AQI forward by a month. This revealed a clearer correlation, suggesting that pollution from new vehicles may take time to show in air quality. Next, I broke this down by fuel type. I expected diesel trucks to show a strong link to AQI, but surprisingly, the correlation was negative. Then I thought maybe more petrol vehicles are being sold now, but the data showed otherwise. Petrol registrations were around 13,000, while diesel vehicles were around 23,000, nearly double. Yet, petrol vehicles had a stronger correlation with AQI, likely because they are more common in urban areas, where emissions affect air quality more directly. In the petrol registrations versus AQI chart, the trends align closely, confirming this relationship. So, air pollution tends to increase with vehicle registrations, especially petrol vehicles, though the effect may be delayed. Surprisingly, diesel trucks didn't show a strong impact, possibly due to better emissions control. These findings show that vehicle type and location matter more than just the total number of new registrations. I used dual axis line plots to clearly show these time based relationships and avoided pie, hist, and box plots since they aren't suited for time series trend analysis. Through this case study, I have shown how vehicle growth, air quality, public health, and population density are all deeply connected, but not always in the ways we expect. More vehicles on the road don't always mean worse air quality, and even highly populated regions can maintain decent air if the right systems are in place. Similarly, pollution related health issues don't appear instantly. They often follow with a delay, and certain pollutants like PM10 and PM2.5 are especially dangerous. I also found that it's not just about how many vehicles are registered, but what types and where they are used. Petrol vehicles, even though fewer in number compared to diesel, seem to have a stronger connection to urban air quality problems, likely because of their concentration in crowded areas.